Hello and thank you for attending our talk. This is Konstantinou, an assistant professor of electrical computer engineering, and I'm delighted to tell you about our work on harnessing the power of distributed energy resources for secure communications in electric energy systems. The other co-authors of this work are Zografopoulos and Ospina, and we are part of the Decision and Secure Systems Lab at the Center for Advanced Power Systems, Florida State University. Let me start by saying that electric energy systems are undergoing significant changes to improve system reliability and accommodate increasing power demands. Over the past years, electric energy systems have diverged from a unidirectional generation and transmission model towards a more distributed architecture that supports traditional generation resources as well as distributed generation such as PV and wind, and distributed storage sources such as battery and thermal energy storage systems. This transformation is enabled due to the introduction of information and communication technologies, automated control systems, remote sensing, and embedded IoT devices. However, the information and communication technology devices enabling such cyber-physical energy system transformation expand the threat surface of the energy infrastructure. The vulnerabilities within such devices can be ported to the industrial environment, creating potential entry points for malicious adversaries that focus on disrupting cyber-physical energy system operations. Among several security concerns are ones that relate with insecure communication protocols, improper in terms of bugs and vulnerabilities implementation of protocols, the constraints related to the economic cost and feasibility of updating and upgrading existing power grid equipment, as well as the devastating consequences an attack would have on the electric energy system from generation to end consumers. In this talk, our focus is how to enhance the security of the cyber-physical energy system infrastructure by presenting a solution as a bolt-on security extension that can be implemented on existing industrial communication protocols. The application focus for our security framework is on distributed energy resources. As the electric power grid advances towards a decentralized architecture, distributed energy resources, or DERs, are becoming more prevalent all over the globe. According to North American Electric Reliability Corporation, a DER is any resource on the distribution system generating electricity. Examples include PV systems, electric vehicles, wind turbines, which are often bolstered by energy storage solutions such as battery energy storage systems, fuel cells, and flywheels. DER generation capacity is expected to reach 530 gigawatts by 2026. Despite the various benefits of DERs, including optimization of power grid resources and bidirectional energy flow, existing communication standards and protocols between DERs and grid utilities or aggregators, lack of cybersecurity standards, can be outdated or insecure, and embedded devices supporting such communications, despite being resource constrained in terms of computing resources, can be maliciously attacked by adversaries. In terms of DER communication protocols, an overview of the existing DER protocols along with their encryption authentication requirements, type of information, type of transmitted data, etc. are shown in this slide. Although new protocols such as IEEE 2030.5 feature cryptographically secure and authentication properties, there is a plethora of already deployed grid devices utilizing insecure or outdated communication protocol versions. For example, more than 75 of North American utilities employ IEEE 1815 Distributed Network Protocol or DNP3 for supervisory control and data acquisition. DNP3 vulnerabilities undermine not only the security of the communication channel, but also the security of devices relying on this protocol. Recently, DNP3 received updates to conform with interconnection interoperability standards such as IEEE 1547-2020 and features security properties similar to newer protocols. However, the protocol has still significant drawbacks and legacy devices still remain a valid concern. As with most cybersecurity problems, there is no single silver bullet which can address all attacks. In this work, we provide a security extension that can enhance utility to DR communications while requiring minimum redesign efforts. We aim to improve the communication security of DR interconnected systems from the lowest level of abstraction. Specifically, we leverage the inherent cell entropy from battery energy storage system enabled DR devices to develop a security primitive which can be incorporated in DR communications and support secure authentication. Our framework, named DERAUTH, secures the measurement and control command data issued to DRs. It provides a security extension that can be retrofitted to any battery storage enabled grid asset which uses DNP3 with minimum redesign requirements, serving as an authentication layer on top of the DNP3 protocol stack. A high-level overview of DERAUTH framework is presented in this figure. It operates using a challenge-reply scheme between the DNP3 master and the DNP3 outstation devices which are located on the DR side. It requires DR outstation devices to be authenticated before control commands can be issued from the DNP3 master. The authentication process leverages the intrinsic characteristics of the battery energy storage system lithium-ion battery cells to generate entropy, and specifically cell voltage and state of charge measurements and their inherent randomness caused by the unique lithium-ion physical properties due to their manufacturing process. To summarize, we developed and ported a battery storage-based authentication scheme into the DNP3 protocol stack. We utilize lithium-ion battery measurements factoring the real-world discrepancies for the secure authentication process, and we provided the implementation details of the design which can be ported in any DNP3 assisted industrial control environment, reinforcing communication security. In order to evaluate DERAUTH, we have developed a proof of concept implementation in which lithium-ion battery cells are used as the battery energy storage system of DERs. The setup provides the state of charge and voltage measurements of cells with a maximum error of ±1%. To attain the highest possible accuracy, each battery cell is subjected to a learning cycle. The cycle involves a full discharge for the fuel gauge module to accurately calculate each cell's impedance. The setup is presented in the upper left figure of this slide. Besides the voltage and state of charge discrepancies between identical lithium-ion cells as the number of cycles and ages increases, the relationship between state of charge and voltage values is also non-deterministic, as presented in the bottom left figure of this slide. In our design, the multiple lithium-ion cells constituting the battery energy storage system of the DR are leveraged towards entropy generation. In other words, the voltage and the state of charge of each battery cell are utilized towards the development of DERAUTH. For the evaluation of DERAUTH authentication process, we implement a testbed setup where two computing stations communicate via DNP3 as master and outstation. The right figure of the slide depicts the overall top-level diagram of the test setup. The master and outstation devices are running modified versions of DNP3 using the open source OpenDNP3 library, which is an open source reference implementation for the DNP3 protocol. We have extended OpenDNP3 to integrate the DERAUTH challenge reply mechanism and support an SQLite database to store the temporally challenge reply values exchanged during authentication. In this implementation, the DNP3 outstation is modeled as an agent that interacts with the battery energy storage system, in other words the DER, and the master DNP3 device is modeled as an agent that sends the corresponding charge-discharge set points to the outstation distributed energy resource. Experimental results implemented on the OpenDNP3 stack validate our scheme using battery data generated by lithium-ion cells. To assess the operation of DERAUTH within the test setup presented in the previous slide, A modified version of OpenDMP3 integrating DERAUTH is deployed in two different computers connected via an Ethernet switch. The DMP3 communication protocol runs over TCP/IP, and the master and outstation are configured to interchange 64-bit float analog values. In this case study, the master device initiates the DERAUTH authentication process every time it sends a new setpoint command to the outstation controlling the DER. Specifically, in our scenario, the DERAUTH authentication challenge is predefined to occur 5 seconds before the master sends the corresponding operation command to the respective outstation. Although a 5-second interval is selected for this case study, any other value could also be used depending on the operational requirements. The figures in this slide present the voltage and state of charge measurements from the two cells used in DERAUTH. The total simulation time is 5,000 seconds, and 4 battery operations are requested by the master controller. These operations are a 10-watt discharge request at 500 seconds, a no operation request at 2,000 seconds, a 10-watt charge request at 3,000 seconds, and finally a no operation request at 4,500 seconds. At each of these points, DERAUTH is executed before 5 seconds the setpoint command is issued. I would like to conclude by saying that the takeaway point of this presentation is that security in modern cyber-physical systems is a major concern. The communication protocols employed for DER management and control in electric energy systems lack sophisticated cybersecurity features and can compromise power system secure operation if malicious control commands are issued to distributed energy resources. To overcome authentication-related protocol issues, we presented a security extension that can be implemented on DNP3 protocol. That brings me to the end of my presentation. You can find more information of our work as well as contact details on our lab website shown in this slide. Thank you for your attention and thank you for listening.